Alright team, welcome to our 18th lecture, and today we will be covering shortest path and all shortest path. We will also learn what minimum spanning tree is, but I wanted to divide the class into two parts because for the best algorithm, like most efficient minimum spanning tree algorithm, it would be great to cover disjoint sets as well. So we will have a follow-up lecture on Monday or Tuesday in which we will cover disjoint sets first and then minimum spanning tree. So, let's start with shortest path. The problem is, we are given a graph and we want to find the shortest path, which is basically a path in which the total sum of the weights of edges is minimum from the source node to the destination node. So, let's start with the easy version first. Let's say in our graph, all the weights have edge 1. Sorry, all the edges have weight 1. Then how can we find the shortest path? Yes? BFS. Like basically we can start from the start point, from the source node, and then we can run BFS. And in the first iteration, what will happen is, like if we start from 0 and our aim is to reach to 7, in the first iteration, 0's children are 1 and 3. And these two are going to be inserted into our queue with distance 1. And in the second iteration, let's say first we get 1, 2 is going to be inserted with distance 2. And after that, since 0 was already visited, we are not going to insert 0 into queue again. And we are done with 1 at this point. And now we are processing 3. And 3 has the first child 0. Since 0 is already visited, we don't do anything. And the second child 4. 4 is not visited yet. Therefore, 4's distance is 3's current distance, which is 1 plus 1. So it is 2. And 7's distance becomes 3's current distance is 1 plus 1, which is 2. And since we reached to our destination, there is no point continuing execution because BFS guarantees us that whenever we find the first path to a destination, it's actually the shortest one. Any questions about this? Why BFS is working for a graph in which all the edge weights are 1? Is it clear to everybody? Okay, cool. So, how about the edge weights are not 1, but they are all positive integers? Any other ideas? Let's think about it for a minute.
BFS might not work in this case because the first distance that is the destination, the edges may have larger weight and the longer path with less edges may have a shorter sum of weights. So
Yes.
better together.
Yes.
So we may need to explore every path and
So like basically what I'm getting from your answer is BFS does not work if we use it as it is. And it would be nice to see it on an example, I think. So let's try to come up with a graph in which BFS is not going to give us, like with the first path, it's not going to give us the shortest distance. Let's say we have 1, and then we have 2 here, and then we have 3 here, and this edge weight is 1, and this edge weight is 99, and like from 1 to 4, there is an edge which is 2, and from 4 to 3, there is an edge 3. So basically from 1 to 3, the shortest path is actually 5, as you see, like if we get these two edges. But if we run BFS, let's say if 2 is the first child that we look for, then we are going to insert 2 with distance 1, and then from, let me see, yes, after that first 2 is going to be executed before 4, and then 2 is going to insert 3 with distance 100, which is definitely not the shortest path. So yes, BFS is not working. But can we actually do slight modification on BFS to make it work? Instead of using a queue, how about we use a priority queue, right? So basically, the reason BFS was working in the version where all the edge weights are 1 is because it is guaranteed that every time when we are doing iteration on a node, like that node has been reached with the shortest path, plus that distance is the shortest distance that is not covered so far. Like all the other distances that are generated in the graph, if they are shorter, they have been considered already. And here we should actually try to apply the same principle. Like basically, if there is a shorter path, that should be considered before than the longer versions. So let's try to execute this. Let's try to execute BFS with priority queue in this graph. Now we start with from node 1. So let's say this is our priority queue. And we inserted 1 with distance 0, because distance from 1 to 1 is 0. And then we insert its children into our priority queue with their corresponding distances. Like we basically pop, it's like normal BFS. We pop, so we don't have this anymore, but we are gonna update on 0. So since 2 is not visited yet, we basically insert 2 with distance 1. And then we also insert 4 with distance 2.
So this is a min heap, right?
What's that? This is a min heap. Yes, this is a min heap. And after that, since we are done with 1, we are gonna pop from our queue, and this time we get 2 with 1. This is gone. Stick it in. Now 4-2 is here. So we visited this guy, we visited this guy too. And right now we are considering inserting 2 children into priority queue. The first children we look for is 1. And since 1 is already visited, we don't do anything with that. And 2's second children is 3. 2's second child is 3. And 2's current distance is 1. And I have an edge with weight 99. So what is going to be the total distance to 3? 100. Therefore, I insert 3 with 100 into my priority queue. And after that, I'm done with processing 2 as well. So I continue with the next node, next value that comes from the priority queue. So I pop the top element, and this time we get 4, 2. So there is no 4, 2 here anymore, so this is 3, 100. And right now I am considering 4 children. First child is 1. Since 1 is already visited, we don't do anything about that. And then the second child is 3. 3 is not visited yet. Don't forget that when are we marking things that visited in this algorithm? When we pop them. Because before popping them, it is still possible that we can reach to them with a shorter path. And when this happens, since 3 is not visited, and the distance of 4 is 2, and 2 plus 3 is 5, what we do is, we go to this priority queue, and then we update the value of 3. Alternatively, you can insert the same node again and again, but in that case, your worst case time complexity is gonna get worse. So, what you should do for a good implementation is, you should have a cross-reference to values in your priority queue so that you can go directly update them. And depending on your language of choice, it might be possible to decrease the priority of values. Maybe there are some priority queue implementations in your preferred language which already keeps this cross-reference, and then can go and update that value immediately. So let me show you these 2 alternatives. In the first case, we do not have cross-reference, so we just insert the node again with better distance. So here I reach to 3 with distance 5, right? And 3 is not visited yet, or 3 is not completed yet. I think completed would be a better word than visited here, because it was visited through 2 before. But it's not, the process is not completed yet. So therefore, at this point, what we do is, like the first alternative, we don't have cross-reference, so we cannot make any updates in the values in our priority queue. Therefore, we insert it again. And we insert 3 with 5 distance. And what is going to happen since this is min heap? It's going to go up. And we will have 3 100 coming down here and 3 5 going up here. So, are there any other child of 4? No. Therefore, I'm done with processing 4. It's marked as completed 2. And I get one more element from priority queue. This time we get 3 with 5. And 3 checks if it has any child who hasn't been completed yet. There is none. Therefore, 3 is marked as completed 2. And this guy is popped. So we have 3 100 here. And I pop from my priority queue again. This time I see that 3 was already completed, therefore I don't do anything about it. And since my priority queue is empty, I am done with processing at this point. And all these distances are minimum. Starting from source node 1, like we basically calculate the shortest path to all the other nodes, all the other vertices. So any questions about how it played out once we don't do any updates? So can you see why we might have a lot of repeated elements in the priority queue this way? Like we can basically put the edges in the order in a way that like the node will always get like better and better results with the help of updates that come from newly completed nodes. So this way we can have like somewhere closer to E elements in our priority queue, which is going to affect our burst time complexity. But if we actually keep cross-reference and go into priority queue and directly update that node's value, what would have happened? Let's see. So we had 3 100 here, right? Let's backtrack. And at this point, we are at node 4. 4 is, we are processing 4. 4 is complete and we are considering its children. 1 was already visited, so we don't do anything. 3 is not completed yet, therefore, I consider inserting a new value for 3, and my current distance was 2. Plus 3, the distance that I'm considering for 3 is 5. And at this point, what I do is I check if 5 is smaller than the current value of 3 in the priority queue or not. So I have cross-reference, therefore I can go from node 3 to the corresponding node in the priority queue. So this way I see that 5 is smaller than 100. And I update 100, I replace it with 5, and then I upheap this node. Like here, since there is only one node, the upheap is not going to make anything. But imagine we could have had a heap like that. Like we have 110 here, and then we have 3 100 here. So at this point, once I do this update to the distance of 3 and I decrease it from 100 to 5, what is going to happen? What needs to happen? We need to upheap, right? So that we can continue having, like satisfying the heap criteria. Therefore, at this point, we can get this cost of log n. Because this time, since we put cross-reference, how many elements can I have the most in my priority queue? N. Therefore, the complexity is going to come down to like n log n, like since I'm applying all these updates. But I think it's going to be like, let's do the time complexity analysis after VCD implementation. Any questions up to this point? Is everybody, yes?
Wouldn't it be difficult to do the heap implementation, like modifying the cross-referencing method?
I wouldn't say so. If you implement your own heap, for example, what you're supposed to do is you should have OM extra memory. And from these cells, you, like, since basically this is numbered in the order of the vertex numbers, it's going to be very easy to come from heap to here, right? So we don't really have to keep any reference. Like, let's say you are considering this heap node, what is the corresponding cell here? It's the first cell, or like cell number 1, let's say, because we have cell number 0 here. So there is no difficulty going from heap to this list, right? But the difficulty is from going here to there, or like going from a node to corresponding node in heap, let's say. Therefore, what we do is we keep cross-reference. So from here, we have like from 3, or like if our heap is like this, let's say this is not the case. From 3, we have cross-reference to this heap node. And from 1, we have cross-reference to this heap node. And every time we apply swap operation, we need to update here too.
By
Yes.
cross-reference, you mean left array will keep the indexes of, for example, in 1, it will keep the index of 1 in the min heap, like 0, for example.
Yes. So let's say, I mean, we are not keeping heap in the tree structure, right? It is, since it's a complete binary tree, it's very easy to keep it in an array structure. Therefore, this has index 0 and this has index 1. And let's say it was 3 and 100 at the beginning. So here in 3, I have 1. And in 1, I have 0. And 0 and 2, they are not in the heap, so we don't care about the values in here. And let's say the update 3.5 comes in. What I do is first I change this to 5. And then I call the up heap, right? And here, whenever I apply a swap operation in the heap, I should also apply the same in my cross-reference array. Like here, 3.5 is going up and 110 is going down after the update. So, which nodes did I switch? Like 1 and 3, sorry, like I asked, which nodes did I switch? 1 and 3, right? From my graph. Therefore, I go here and then I apply the swap operation between their cross references as well. So I say 1 is now in 1 and 3 is now in index 0 in my min heap. Is this clear? So any questions, like if there is something vague or gray, please ask it now.
This would be difficult to track if you're using the heaps of already like established.
Yes, if you are using like already existing heap with no cross reference, it will be tricky to do that because of the abstraction. I don't think you can get this in these numbers easily. Or like when you insert something, it's not gonna give you, okay, so this is swapped with this is swapped with this information.
You
So
could look for the element in log n time, but I don't know if that's any better.
what's that?
We could look for the element in log n time.
How are you gonna do that?
Like, we could,
How do you know whether it's on the left or on the right?
we still take a lot of n time. That's not good. That's not effective.
It's going to take a while time to search, right? Linear search. That's why we are actually keeping the cross reference, right? If it was log n, then you could have said, it's log n, it's not going to cost too much. And the other alternative is like, you can consider having the same node multiple times in the queue. Like if you are looking for not implementing heap by yourself, then what you can do is you can insert the same element again and again, but this time like your verse time complexity is going to be increased. So let's do the analysis after seeing the code for both versions. Then like you will see the trade-off, and depending on your circumstances, you can choose which one you want to go with. But like as you see, under some circumstances, it can be very handy to know the implementation of a data structure for which you already have built-in functions in your preferred programming language. So that's why, like from the beginning, we started with very basic tools. Like we learned how to start fire with just 2 wood sticks, and now we are using the lighter. But sometimes still using the wood sticks can be handy.
Sometimes the lighter runs out of gas.
Yes.
On the first execution, instead of waiting for a heap to be exhausted, what if we mark it? What if we end our execution once we pop an element with a desired destination?
Yes, like if you are given, yeah, definitely you can add that shortcut, because like if you look at the execution here, basically we find shortest path from given source to all the destinations. And if you are using priority queue, whenever you pop the element, if that popped element is your destination, there is no point continuing execution after that point.
So
Because
in
it's
this case,
guaranteed. What's that?
In this case, we continue to until the heap is to find the shortest distance to all nodes.
Yes, yes.
But if we have a defined destination,
Yes, if we were given destination, we didn't have to do that. Because once you, but this is important, not once we put the node into priority queue. Once it is popped out, it is guaranteed that the shortest path is calculated for that node. Is this clear, guys? Because this is important. Like some people who are just learning this algorithm, they make this mistake. When they put the element into priority queue, they think that it's going to be shortest path. Like we actually had an example. That's not the case. We guarantee the shortest path once we pop it out from the priority queue. Any more questions about this? If not, let's take a look at the implementation. So, initially, we start with initializing the distance with 0, and we create a priority queue. And then we basically mark all the distances infinity and previous node as undefined in this queue. And like basically that's what we add into priority queue. So here in this algorithm we also keep track of the shortest path. Like we are not just interested in the distance, we also keep track of the shortest path. Like how to get there from the shortest path basically. So after that we start execution and we get the minimum element from the priority queue, minimum distance. And for each neighbor of that vertex, we check whether the distance we have so far plus the weight of the edge between us is smaller than what we have seen for this node before. Like look at the line 80. So alt stands for alternative route we can think of. And our alternative route is the current distance of our current node, which is u, plus the edge weight or the length of the edge between the neighbor and the current node. If this is smaller than what we have seen so far, what does that mean? I have a shorter route. I have a shorter path. Therefore, I need to update my existing path. And what I say is the distance is updated with the alternative distance. And right now, the shortest path that I know to V goes over U. That's why I only keep track of the previous node. Like imagine, we start from one node and we are trying to go to another node. If I have a shortest path, is it possible to have a cycle in the shortest path?
No.
Definitely not, right? I mean, one of the edges is unnecessary, I can remove that. So, it is guaranteed that there is no cycle. If there is no cycle, obviously it's a tree, right? I mean, it's actually kind of like linked list, even there is no branching, I mean, if it's between two nodes. So in that case, I can basically have a previous reference to create all the shortest paths. Meaning, I start from 1. 1 doesn't have any previous node because that's the start point. So, 4. The shortest path from 1 to 4 is the direct edge between, right? Therefore, the previous of 4 is going to be 1. And for 2, it's the same thing. Like the shortest path to 2 from 1, it's the direct edge. Therefore, the previous node for 2 is going to be 1. If you remember our execution first, we were considering this edge, right? At that point, we say the shortest path that I know to 3 is 100. And the previous node is 2. Because I came to 3 through 2, right? And when I find an alternative route with a shorter distance, what I did was, okay, so I don't come to 3 from 2 anymore. I found the shorter path. And this time I am coming to 3 from 4. And the total distance is 5. Like as you see, by keeping track of from which node I come to this node, I can basically keep track of all the shortest paths from given source nodes to all the other nodes. Is this part clear to everybody? Because like shortest path, it's like a line, and in a line, every node has previous, right? Except the source one. So just by keeping track of previous, we can basically construct the shortest path for all of the nodes for the given source node. Is this part clear? So now let's get back to the algorithm and continue execution of the rest. So at this point, we are decreasing the priority. This means like updating its distance value. Like if you remember the first path we found to 3, its distance was 100. And then we found an alternative path with distance 5. At that point, we need to update its priority so that it can go up in my min priority queue.
It's actually increasing the priority.
I mean here I think like they think of this priority queue as this is min priority queue. I mean you can think of that way too. Like if you think that the root node has the highest priority, you are increasing the priority. If you think the root node has the lowest priority, you are decreasing the priority. That was the language that they used in Wikipedia. I get the quote from the Wikipedia, and I didn't change it. But I think the concept is clear to everybody, right? By decreasing, we mean like its level is gonna go up in the tree, or in the worst case, it's gonna stay, but it's not going down. And once my queue is empty, I basically calculated all the shortest distances, and with the help of previous array that I filled up, I can construct the shortest path for any given node starting from the source node. And now let's think of the time complexity. So how many elements, like how many times this while loop is going to iterate?
H times.
H times? Let's think about it.
H
There is
plus,
only-
H plus vertex times.
Let's think about it. Let's not just talk about, first think about that. Yes.
Vertex times.
Vertex times, yes. Like if you look at here, like every time I pop one vertex, right? And then I'm done with it. And next time, I continue with the next vertex. Therefore, this while loop, other while loop, it is executed vertex times, or n times, or v times. And let's also take a look what is happening inside. So, in the worst case, like if everything is connected, inside I will consider each edge for update. Therefore, I have V coming from the outer loop times here. How much operation do I do? Actually, it's not multiplication, it's plus. The reason is I am not visiting all the edges for every vertex, right? If you think about it, it's like BFS. All the edges are going to be processed only once. It's going to be considered only once whether it's making update or not. Therefore, like inside, I will have complexity of E, number of edges, but at the same time, there is one more call here, which is this priority call. So how many elements can I have in my priority queue the most?
V.
Yes. And what is the cost of decreasing priority or like applying any kind of update to my priority queue?
Log V.
Log V. So basically, I have V elements in my queue, in my priority queue, and at each operation I can basically apply log V, right? Then what is going to be the time complexity here? What's that?
Actually, I think it should be E times log V.
Yes. There is a typo there.
Type
Yes.
because for each edge we can do this decrease priority thing.
So that's why we constructed here. Yes. Any questions about this? But let's think a little more. Maybe we can actually have a tighter bound. I think it's going to be E log V. I mean, at least with this implementation, without any more improvement, for each edge, we can possibly make an update in our priority queue, and in that case, this is going to be the time complex.
Basically, if you find the node, the first time you find the node, it's the longest road, and then the next time it's the second
If
longest.
every time there is an update coming for each edge, then it's going to be like this. Yes. So, any questions about this? And the space complexity is obviously, since we have V nodes in our queue and V array for the cross reference, so that we can apply the updates easily. The space complexity is going to be OV. Any questions? If not, let's continue. And this time, again we are given a graph, but we are not just interested in shortest path from given source to all the other nodes. This time we are interested in all the shortest paths. Given any two node pair, we would like to be able to calculate the shortest path. Or like we would like to be able to return it in all one time, so that we want to pre-compute all of them.
So in this example, for example, 2 to 3 is 6 actually, right?
Yes.
So we can't find it starting from 1. So
Yes.
okay.
Yes. So what is an obvious solution right now for all shortest paths?
Could we maybe once we've collected the shortest paths from one node, then we could maybe reduce them, but I don't know if that's for sure the shortest one.
V plus
Then it's not
E-
obvious. If you're not sure that this is not a solution, then it's not an obvious solution. Yes.
To do the previous computation for each one.
Like basically we have the shortest path code that works from one source node, right? What if I call this for all the nodes? Exactly. So what was my time complexity before? It was V plus E log V, right? And if I call this V times, what's going to be my new time complexity?
Square. VE log x.
So it's like, we can think of this kind of like V cube. So it's going to be dominated by this term basically. Can we do it better?
Maybe we could store shortest path between two nodes, and then we can keep reusing it for next time it's been requested.
Short split for two nodes, and then we can keep reusing it.
If another path requests that path, let's do it, and then we can use that instead of having to calculate again.
Yes.
Still would be a little improvement, but I don't know if it makes a lot of difference.
So this is undirected graph, right?
Undirected, yes, all the graphs that we
So
have
for
seen.
example, in here, if we try to find the distance from 2 to 3, we can basically say that 1 to 2 plus 1 to 3 equals to its minimum distance, maybe. Not all the time.
Yes, but I mean, you guys are getting the head of the real algorithm. So the real algorithm, it's not super trivial to come up with in short amount of time, but you guys are getting sense of it. So we have already considered the time complexity of this, and now let's look at the all shortest path algorithm here. So basically, the algorithm works like this. We are using first k node as intermediate nodes to check if we can find a shorter route with the help of them. So initially, I have all these distances, right? All the edges are the shortest path that I know between any node pair. So from 1 to 4, what is the shortest path that I know? 2. From 2 to 3, what is the shortest path that I know?
I don't know.
99 at the beginning. We didn't run anything. If there is an edge in between, then we know that it's 99 at the beginning. Like without doing any kind of calculation, at least I can tell if there is an edge between these two, that's gonna be the distance between them, right? So we start with this. And then what we do is, what if I use another node as an intermediate node to get a shorter path? So now, like, from 1 to 2, 1 to 4, 1 to 3, I have all these shortest paths, right? So now let's consider this idea. First, I'm going to use 1 as an intermediate node. What is the known shortest path from 2 to 4 at the beginning?
3.
It is 0. I mean, or infinity.
Infinity.
Because at the beginning, we only know about edges in the graph. So from 1 to 2, or actually it's better to just create the matches. So we can see it easily. And from 1 to 2, I know that it is 1. And 2 to 1, it is 1. 2 to 3, it is 99. 2 to 3 is 99.
3 to 4, it is 3. 1 to 4, it is 2.
1 to 4, it's 2. 4 is 2. So this is the initial knowledge that I know. And after that, what I'm doing is conceptually, first I am considering one as the intermediate node, and the others are infinity. This is what I know at the beginning. And then I say, okay, what if I use 1 as an intermediate node? From 2 to 4, what is my current node distance? Infinity. And how about using 1 as an intermediate node and creating 2, 1, 1, 4? What is the total distance for this? What is 2, 1? It is 1. So this is 1. What is 1 for? It is 2. Is 3 less than infinity? Then now I have a shorter path. So 2 to 4 now becomes 3. And we can have update 4 to 2 at the same time too.
So if we couldn't find, for example, we chose 1 and it was actually, there was a edge between 2 and 1 and 1 and 4. But we could have chosen a node that doesn't have an edge to 2 or 4. For example.
I don't understand the question. Can you repeat?
So we chose 1, right? And
At the beginning we start with 1 and then we are going to use 2 as an intermediate node, 4 as an intermediate, sorry, 3 as an intermediate node, and finally 4 as an
what I
intermediate.
mean is, when we chose 1, actually we didn't know that 2 and 1 has an edge between, right?
If it doesn't,
When we chose 1, no, we didn't know, yes.
And if it wasn't the case,
If the, for example, if it wasn't the case, then you would have seen infinity. And you would do like calculation with infinity plus 2, whether it's infinity plus 2 is less than infinity or not.
okay.
Since it's not going to make any update. Like, did you guys understand Murat's question? Like, imagine, for example, let's actually consider that. So there is no edge between 3 and 1,
let's
right?
add one more node 5, just for
I
example.
don't. We already have 1,
Okay.
3. So there is no edge between 3 and 1. So now let's consider if we can update the distance between 3 and 4 by using 1 as an intermediate node. So right now we are considering 3, 4's current known value, which is 3, versus 3, 1, 1, 4. What is the distance between 3 and 1? Infinity. What is the distance between 1 and 4? 2. So basically I check if infinity plus 2 is smaller than 3 or not. Since it's not smaller, I don't make any updates. So we actually checked it for, like basically what, yes, we used 1 as an intermediate for 2, 4, and now we used intermediate 1 as intermediate node for 3, 4, and there is one more that we should use, which is 2, 3, right? There is like 2, 4, let me see. So except 1, I have like 2, 3, 2, 4, and 3, 4. So right now, I already checked 2, 4. And we also checked 3, 4 right now, right? So there is one more. We should also check 2, 3. What is 2, 3's current value?
99.
99. And if I use 1 as an intermediate node for 2, 3, what is the distance between 2 and 1?
1.
What is the distance between 1 and 3? Infinity. Therefore, I am checking if 1 plus infinity is less than 99 or not. It's not, therefore I don't update 99. So by using 1 as an intermediate node, I basically updated 2, 4 distance, and the others, they were shorter. Therefore, I didn't apply any updates. So in the next iteration, if we look at this for loop here, like first we use 1 as an intermediate node, and then we check if using 1 as an intermediate node helps us in any cases or not. And if it does, then we just do the update. And in the second iteration of this, we check. What if I use 2 as an intermediate node? So let's try to make it a little more systematic. Sorry, today I'm not using the whiteboard very well. So we are done with using 1 as an intermediate node. So now we are going to check using 2 as an intermediate node. Which other pairs do I have except 2 in this graph? Like I have 1, 3, 1, 4, and 3, 4. Right? So what is current distance of 1, 3? Infinity. What is the current distance of 1, 4? What is the current distance of 3, 4? 3? Okay. So, right now, first we are checking if by using 2 as an intermediate node we can beat infinity or not. What is the distance between 1 and 2? 1. What is the distance between 2 and 3? 99. Oops, sorry. 99. So, is 1 plus 99 less than infinity? Yes. Come on, you are a solution. Since it's less than infinity, I do update 1 3 and replace it with 100. And also, I do update 3 1 and replace it with 102. So, let's continue with the second one. For 1 4, the best known solution is 2. And now we consider 1 2. 2 4 is beating this or not. What is 1 2? 1 2 is 1. What is 2 4?
3.
3. So 4 couldn't be 2, therefore I don't make any updates. And finally, I consider for 3 4 using 1 as intermediate node. What is the distance between 3 and 1?
100.
100. And 1 and 2?
1.
101 didn't beat 3, therefore I didn't make any updates. So we are done with using 2 as an intermediate node too. Now the next one is using 3 as an intermediate node. So
3 and we are checking 3 and 4, right?
what's that?
On the last execution. It was between 3.
Oh yeah. Sorry. This was supposed to be 4. Yes, thank you very much. And what was the distance between 1 and 4? It was 2. I mean, again, it couldn't beat the result we had, but you're right. It has to be 4. Thank you. So now we are done with using 2 as an intermediate node, and we are going to use 3 as an intermediate node. So which other pairs do I have?
1 2 1 4 2.
Yes. What is the current known best for 1 2?
1
For 1 4?
2
For 2 4?
3.
So we are trying to beat these by 1 3 2, 1 3 4, and 1
2 3.
sorry 2 3 4. What is 1 3?
100.
100.
What is 3 2?
99.
So this couldn't beat, no updates. What is 1 3? 100. What is 3 4?
3.
So 103 it couldn't beat 2, and 2 3 is
99.
99, and 3 4 is
3.
3.
100.
Again, like no updates by using 3 as an intermediate node. And finally, we are checking if we can make any upgrades, we can find any shorter routes by using 4 as an intermediate node. And now I have pairs 1 2, 1 3, and 2 3. What are the current best node? 1 for 1 3, 100, and for 2 3, 99. All right, this is going to be a fun. So, now we are considering 1, 4, 2. What is the distance between 1 and 4? What is the distance, or it's easier to write it like it's 3. What is the distance between 4 and 2? 5 couldn't beat 1, therefore I couldn't get any update
4
from
and 2
this
is
one.
3 actually.
What's that?
4 and 2 is 3.
Okay, so 6 couldn't beat 1, therefore no updates. And here we have 1, 4, 3 path. What is the distance between 1 and 4? What is the distance between 4 and 3? Is 5 less than 100? Yeah.
I guess so.
Keep guessing.
So we get update from this one. And finally, we are considering using 4 as an intermediate node for 2 trees, best distance so far. 2, 4, 3. What is the distance between 2 and 4?
3.
What is the distance between 4 and 3?
3.
3 plus 3 is 6. Minasir. 6 is less than 99, therefore I do the update in my table. These guys become 6, 6. Did we find all the shortest paths? And actually, are you guys able to see that like we are not just considering using only one intermediate node? Because every time, like for example, if 1 tree was updated, let's say we have more nodes in our graph. Like let's say 1, 5 was updated with using 2 as an intermediate node. Like the path was actually more like 1, 2, 5, right? And then in the future, let's say I found shorter distance between 2 and 5 by using 3 as an intermediate node. So this would be like 1, 2, 3, 5. So the conceptual paths that we are considering can have more than one intermediate node. And this is because like when we use 1 as an intermediate node, we make some updates. And on top of that, if you make some updates using 4 as an intermediate node, you can actually consider some paths whose length is 4. This is such a simple algorithm, but it's a very powerful one. So there are 2 things I want to discuss about this one. Is everybody able to see the for loops here? So right now this is clear and cube, right? Can we make it not asymptotically better, but practically better?
When progressing through the nodes, if we have greater weight than we have before, we have to stop.
If we have
Greater this node, the weight than the saved one, we have to stop.
like, are you gonna break from the loop?
No, I'm just, for example, if
Like let's write the code on the whiteboard. I think it's gonna be easy to work out.
minus weight accelerate.
So this is the code. Yes, Faisal, right now, like I am basically, I kind of understand what you are saying, but it's a little hard to apply in this execution, right? So I am actually looking for practical suggestions to make less computation in this for loops. Actually, there is a hint on how we execute it on here. Like as I said, we are not going to improve our asymptotic time complexity, but we are going to improve our practical time complexity. Meaning if we divide it by 2, for example, It's going to be practical improvement, right? But it's not going to change the asymptotic time complexity. Yes?
J could possibly start from I.
J could possibly start from I. Yes? And then I, or like since the self distances are already 0, we can say I plus 1. And is this going to be correct if we just do this?
If you are going to
We will
I
need to-
starts from K plus 1.
I starts from K plus 1. Is it going to work?
I have an idea.
Then have an idea.
Because I didn't understand this either. Why does it work?
Like right now, is this working? Let's start with this. This is 1. Is this working?
Yes.
Okay. So right now I didn't say that this is working.
Okay. I thought it got
I'm
accepted.
saying like, no. That's a good start, but do we have to make any modifications?
It's counter.
What's that?
We have to see if it's counter.
Yes. So basically we should say this Ji is equal to this Ij is equal to this. So there is no reason to consider them separate, right? If the graph is undirected, which is the case here, if the graph was directed, we cannot make this pruning. But since the graph is unweighted, we can do that. And this way, the inner execution is not going to be n squared, but we will have a division factor. So is everybody clear with this pruning? So we made practical improvement. And now let's consider Murat's idea. So let's move this to 1. Actually, this is also related with, can we change the order of loops? And we make this K plus 1. What will happen?
There's no proof that it could connect only the elements after it, so we can't really tell if. I mean, it could, for example, if our K is 2 or something, it could connect any element from 1 before it or from after it, so we can't really tell. So
Yes, therefore there is no correctness guarantee here. So if you remember, with the help of the first loop, what we are doing is we are considering kth node as an intermediate node. And if we make it like this, like without this, right? If we make it like this, what happens is we never consider node k as an intermediate node for nodes between that starts from something less than k and that is greater than. Yes.
So since J, okay. From I to J, yeah.
I didn't even understand at the beginning that K is actually the intermediate.
Yes. K is the intermediate one.
Same. Wait, if it was K plus 1, since J starts from 1, will it work regarding
If you only have this, it's not gonna work.
is Ji is equals to Ij?
This time it would work.
K plus 1?
yeah, makes sense.
Like because basically you consider every pair again. How about if we change the order of loops?
You mean K?
What's that?
Swapping this K? Which order?
Like we, for example, execute K here and I on the top.
This would mean I is connecting K and J, so we need to modify the inner.
We are not modifying it, we are just, that's the question. I mean, if we are modifying, come on. You rename the
I'm
variables.
just saying we need to modify it to make it right.
I think it would still work.
And by logic it should work.
By logic.
I mean, K didn't change, I didn't change, J didn't change, so why shouldn't it work? I mean,
I mean, we're just still doing the.
What is your, like, what is here, like, what is your intermediate node?
I would be the intermediate one.
Your intermediate node is K, right?
Yeah.
no,
That-
Right now, I know.
And I mean, by this, K is your intermediate node, right? So K is your intermediate node. Are you considering K as an intermediate node for all the combinations in the right order? Is there a right order? First, that's the question. There is no right order. If you are considering it for all the pairs, it's gonna get worked anyways, right? How about this?
This will work. I am quite sure.
Quite sure.
Yeah, you know, just gamble. This will work because it doesn't matter anything. Nothing matters basically. Nothing matters. If you make it I plus 1, we should add this GI.
Last one.
All right.
We're
So
playing all the combinations.
I give this as an homework. Okay. So after implementing all shorts path, please try it in a big array, like big graph, to see if you always produce the same order with all these little plays that we have made. Not all of them are working.
This will definitely work. Try this. Try this.
And finally, we are going to learn the definition of minimum spanning tree today. As I said, for the optimal algorithm, it would be great to know disjoint sets. And in our next lecture, first I want to talk about disjoint sets and then go into minimum spanning tree. But there is no harm in learning the definition of minimum spanning tree. And before minimum spanning tree, is there something that we should know? We should know about the spanning tree, right? Otherwise, how are we going to know the minimum one? Yes. So, a spanning tree is a tree that connects all the nodes in the graph with a subset of edges. Let's say this is our given graph. Is this a spanning tree? If we get the graph completely?
Yeah.
No, it's not a tree.
Oh, okay. Yeah.
Yes. But if you remove any of the edges, but if you remove only one edge, then they are all going to be spanning trees for this graph. Basically, the tree needs to connect all the nodes in the graph. That's the only condition for spanning tree. And when we say minimum spanning tree, we actually mean that the spanning tree whose total of weights of edges is going to be minimum. So, for this example, I think it's very obvious. We have only one minimum spanning tree, which is getting this 1, 2, and 3. Like once we remove the maximum edge for this graph, we get the minimum spanning tree. But like 1, 99, 3, this was a spanning tree, but it wasn't minimum. And I say S spanning tree, the reason is there can be multiple minimum spanning trees. Like imagine if all the weights were 1, or if all the weights were 2. There are 4 different spanning trees, right? You can remove any of the edges, and the remaining ones are going to be minimum spanning trees. So it's like dynamic programming solution. We can say an optimal solution, but we cannot say the optimal solution. So it's the same here. We can say a minimum spanning tree. There is no guarantee that it's going to be unique. Yes?
I don't get if it's the cycling. Is this not a spanning?
This is spanning graph. It's not a tree, right? First off.
Oh,
Yeah.
okay.
So what I was saying is you can remove any of the edges here, but only one edge is going to be removed. Like for example, 1, 2, 3, 4. Like this is a spanning tree for this graph. It's indeed not just a spanning tree, but it's a minimum spanning tree. And another one can be, like we can remove 1, 2 edge, and then 1, 4, 4, 3, and 3, 2. So this is another spanning tree. And also this is another minimum spanning tree.
So if there is an edge between 1 and 3, the diagonal, so that means we can't find the spanning tree. Can you find a spanning tree in this one?
Of course.
You can
Like you don't have to get this edge. Like for example, let's say if this edge was weight, this edge weight was 1, then these wouldn't be minimum spanning trees anymore. Because in this case, the minimum spanning trees have to contain this one edge. Therefore, like then like these are gonna be just spanning trees. So the minimum spanning trees, one of the minimum spanning trees from this graph would be having one tree with 1, and then you can connect all the others with 2s.
And just use
This would be the minimum spanning tree. One of the minimum spanning trees.
we can remove multiple edges, right?
Let's look at the definition, Daniel. Spanning tree is a tree that connects all the vertices of the graph with subset of the edges. It's a tree. Like if it's a spanning tree, it must be a tree, right? It's a tree. And the other condition is it needs to include all the nodes. So now let's take a look. I mean, it doesn't say anything about you can remove these edges, you don't have to remove that edges. No, there is no such thing. Focus on the definition. It has to include all the nodes, it has to connect all the nodes, and it has to be tree. So is this a spanning tree? Like it has all the nodes, right? We have 4 nodes and they are all connected. And is this a tree?
It is.
Yes. Let's look at this one. Is this connecting all the nodes? Is this a tree? That's a spanning tree too, but at the same time, this has minimum total edge weight. That's why this is minimum spanning tree. We are gonna talk more about this because today we are not gonna cover the algorithms, how to find minimum spanning tree. Yes.
So a spanning tree must have v minus 1 edge, right?
Yes.
And
I mean, because you have in a tree with v nodes, how many edges you're gonna have? V minus 1.
and number of spanning trees are basically edge combination v minus 1.
It depends on the graph. I mean, it can be 1 if I just give you the tree.
That means that edge combination v minus 1 is
What? Edge combination?
edge combination of edge and v minus 1.
What do you mean combination
Edges.
of?
number of edges.
Number of edges.
And
V minus 1.
like this?
Yeah.
Probably not necessarily. Yes, I mean, in different graphs, I think you're going to have different structures. Let's think about it. Because you're basically saying, like, I can remove that many edges, but there can be some edges that cannot be removed. Like, imagine this.
Oh, actually, yeah.
Yes. That's
Like here, for example,
I will go up just
Murat, are you listening?
he's trying to get the motion to
Okay.
interview problem.
Okay. So here, all these edges, they are optional. You can remove all of them.
But 1, 2 is not.
But this is not an optional edge. So that's why I think it's going to be hard to get with that kind of formula that fits to all the graphs. Okay, any questions about minimum spanning tree or spanning tree? I mean, we are going to cover this in another lecture, so don't worry about if it's not super clear in your mind. But let's just get familiar with the definition. Then we are going to go into details of how we can find minimum spanning tree in an efficient way in our next lecture. And before we finish, so the questions are coming for shortest path and all shortest path. And as always, we are going to finish with the code of the day. And today's code is, judge nothing, you will be happy. Because we usually become unhappy by our judgments. That's true. Forgive everything, you will be happier. Because sometimes some people are going to do wrong things. And in that case, if you forgive them, you're not going to feel bad about their mistakes. So you're going to be even happier. Love everything, you will be the happiest. So I think it's also very obvious, right? And you guys are in Ethiopia, and Ethiopia is the country of love. So I think we can learn it from you guys. Thank you very much.